Designing and then constructing a circuit is one of the most tedious yet rewarding things you can do in the field of electronics. However, what if you could just break out a pencil, draw a circuit on a piece of paper, and have it work? By using basic drawing materials such as a graphite block or a pencil, we're going to be able to draw a circuit out on a piece of paper, hook a battery up to it, and actually power an LED light. In the early 90s, Forrest Mims unleashed several cool experiments on the world in his book called Science Projects. This first example was included. If we draw out a nice thick line on some paper, the graphite in the pencil will actually work as a resistor. And as you may or may not know, a resistor basically restricts the flow of electrical current. Graphite itself is a pretty terrible conductor of electricity, but it will carry just enough to light up an LED when the source is a 9-volt battery. Now, an LED typically requires 3.5 volts to power up, and going too far above that could nuke the light itself. Due to the resistive properties in the graphite, we're actually able to cut that power flow down to a more reasonable amount, which will power the LED safely. You'll also notice that the LED gets brighter and darker depending on how close we get to it. That's because we've actually created a variable resistor. But what if we wanted to make an actual circuit out of this? Would the resistive properties prove to be too great, or could we still transfer enough energy to light and power it up? So let's give it a try and find out. After doodling a little pencil maze, I poked the LED into a positive and negative terminals. I lowered the lights, and as you can see, it powered right up. Obviously, some minor adjustments were needed to get everything to sit right, but the result was a paper circuit. Not being satisfied with just that, I wanted to up the ante just a little bit more and see if I could MacGyver myself a flashlight using just these materials. After scribbling 2 lines across the paper, I decided I would roll it up into a cone. After that was done, I made some minor adjustments and clipped it out so that the graphite would be visible at both ends. Then, adding a little bit of tape, we were able to seal it up. Now I just took a little bit more tape and added the LED to one end, and then clipped the batteries to the other end. Lumos, it worked pretty well considering what it was made of. I even discovered a monster lurking in the dark. So I thought that was pretty cool. MacGyvering a flashlight is always at the top of my list of boredom killers. Anyways, last week we told you we'd be giving away our solar phone that we created in the last video. Well, we took all the names down in a sheet and we picked one at random, so congratulations to Rob H. from Richmond, Virginia. That being said, I want to thank Netflix, which is one of our biggest supporters here at Scientific Tuesdays. They've got over 23 million members and they're the largest subscription service streaming TV shows and movies directly to you. When you become a Netflix member, you can instantly watch as many movies as you want on your PS3, your 360, your Wii, even your mobile devices or tablet PCs. If you've been wanting to check it out for a while, but maybe you're on the fence just a little bit, well, go to netflix.com/science. You'll get the Scientific Tuesdays special, which is 30 days free. You really have nothing to lose here at all. So check it out and you're gonna love it. Thanks for tuning in, everyone, and we shall see you next week.
So this is my little setup to make some table salt, also known as sodium chloride. So just from the name sodium chloride, you can pretty easily see that it has 2 major components, sodium and chlorine. On their own, both elements sodium and chlorine are pretty reactive and dangerous. However, interestingly enough, when they are combined, they form a nice edible salt. This is an interesting demonstration that shows how drastically different the properties of a compound can be compared to its components. So for the first step, I'll cut off a small piece of sodium that I'm going to be using for the reaction. Sodium metal is actually quite shiny, but it quickly reacts with air and moisture and forms a white coating. You can see a bit of the shininess after it's cut on the bigger piece. The liquid that you see dripping off the sodium is mineral oil, which is what the sodium is stored in. This is my chlorine generator. Inside the flask is chlorine pool pellets. I then poured hydrochloric acid into the flask and it reacts to produce chlorine gas. As you can see, the chlorine has a faint greenish yellow color. The top is blocked, so the chlorine is forced down the hose. The hose leads into a larger flask with sand at the bottom. The sand is at the bottom to prevent the glass from cracking from high heat. Inside the flask is then dropped a small pellet of sodium. This is half of the piece that I cut off in the earlier shot. A little water was added to get the reaction started, but I think I added a bit too much. The white cloudiness that you see is a suspension of really small particles of sodium chloride. The white stuff on the walls is also sodium chloride. When a lot of the sodium chloride cloud has dissipated, it's a lot easier to see a lot of the white sodium chloride all around the flask. I decided to try it again, but this time putting much less water to see what would happen. It took a bit longer to get started and there was more flame, but it wasn't too impressive. It was pretty short-lived and it wasn't very spectacular. Maybe it would be better if I used more sodium. The interesting part is that with the second run, since the sodium stayed in one place, I was left with a solid block of sodium chloride at the bottom. Unfortunately, because the sodium was reacted in sand, it's highly contaminated with it. So you can see here that when it's broken up, that a good portion of it is sand. I really did want to get the sodium chloride as pure as possible, so I opted to carry out the experiment again using the second most common method. This involves heating the sodium up until it melts and lowering it into an atmosphere of chlorine. This way, I wouldn't need to use sand and I could probably get a much purer product. Because no sand was required, I opted to do the lazy method, which is putting the chlorine pellets at the bottom of the flask and simply pouring hydrochloric acid in. To lower the sodium in, I made somewhat of a ghetto little contraption which involved a broken test tube and an alligator clip. The sodium was placed at the bottom, and then using a torch, I melted it. I heated the sodium until it ignited, but when I lowered it into the chlorine, it went out, which was quite surprising for me actually. Despite it going out, all of the sodium that was exposed to the chlorine became nice white sodium chloride, but unfortunately this is not the spectacular reaction that I was expecting. I took the sodium back out and I heated it a lot until it was molten red. This time, when I placed it back into the chlorine, it was a much more spectacular reaction. The sodium burned really bright and it turned my Erlenmeyer flask into a lantern. From demonstrations and other resources that I've seen online, I honestly expected this reaction to last no more than a few seconds. I'm not sure if I just used more sodium than the other demonstrations, but the reaction seemed to go very vigorously and bright for at least a minute. Now that the reaction had died down, it's possible to see the reaction going on inside the broken test tube. Compared to the other method where it was ignited using water, this method produced a lot more sodium chloride smoke. The test tube was coated in a thick layer of nice white sodium chloride. I tried to scratch off as much as I could, but it's honestly very hard and stuck very tightly to the glass. When it's poured out, you can see that this product is much cleaner than the last run. This sodium chloride was surprisingly fluffy, maybe because it wasn't contaminated with so much sand. Although this product looked nice, white, and clean, I still highly advise that you don't sprinkle this onto your food.
Can you tell me what would happen if I were to keep this glass of water in the open air for some days? It will become acidic. Did you ask how? Air contains carbon dioxide and this will dissolve in water to form carbonic acid. Carbon dioxide is an oxide of carbon, which is a nonmetal. And just as carbon dioxide forms an acidic solution on dissolving in water, so will other oxides of nonmetals. To verify this fact, we will need sulfur powder, a nonmetal, red and blue litmus papers, test tubes, burner, and a glass of water. Take sulfur, which is a nonmetal, in a test tube. Heat the test tube. The sulfur on heating will combine with the oxygen in the air to form an oxide called sulfur dioxide. Observe the fumes of the sulfur dioxide gas coming out of the test tube. Hold wet pieces of red and blue litmus papers in the gas. We observe that red litmus remains the same while blue litmus turns red. So when sulfur dioxide gas dissolves in the water in the litmus paper, it forms an acid. Thus, all non-metallic oxides, when dissolved in water, form acidic compounds. Did you know that sulfur dioxide, formed in various industries, is a major pollutant in the atmosphere? When it rains, this gas dissolves in the water and turns into an acid, and that is called acid rain.
Okay, this experiment is to remind you of how we make a salt from an insoluble base. In this case, it's copper oxide and an acid. Now, notice the acid is an irritant, so as usual, you have to write about a risk assessment, you talk about lab coat, goggles. If you spill anything, you mop it up straight away. Spill it on your hands, you wash it off with water. So, I'm going to measure out 25 centimetres cubed of my acid. I'm going to put it in a beaker, and then I'm going to add my insoluble base. In this example, it's copper oxide, which is a black powder, and not a lot seems to happen, I'm adding an excess, more than enough. That means that we can guarantee all our acid is going to be used up in this process. You might say, well, if all the acid is used up and you've got excess base, that won't be neutral. But in fact, it will be, because our base is insoluble. Now, next step, to speed up my reaction, because you can't actually see anything happening there, is to heat it up. So I'm going to give it a bit of heat and stir it at the same time to stop it spitting. And an exam question often asks, why do you heat the solution? Why was the solution heated? Nice simple answer: to speed up the reaction. You remember all the ideas you have to say about particles and why heat speeds up a reaction. I'm going to stop heating that now actually, because it's already heated up quite quickly. Remember, if a question asks you why does heat speed up a reaction, it's the case of the particle is going to move faster, they'll have more energy, so they will collide more often, and even more importantly actually, they will collide with more energy or more impact. Now, you might just about be able to see a hint of colour, although it probably still looks quite black. There's a tiny hint of blue there. Here's one I prepared earlier, which is very blue because the reaction is complete. Now, as I say, I've got excess copper oxide, the black solid that's making that very dark. So my next step is to filter it. And this is how I get rid of that excess. As I say, because we've got excess, we can guarantee that the acid has been used up. Pour the copper solution. You can see there's a lot of black solid left behind, but we're filtering nice and rapidly there, and within a few seconds we should have a nice solution of copper sulfate. It's a solution, so as in the last video, if you want to change your solution into a solid, if you want to get crystals of copper sulfate, you've now got to evaporate off the water. Now, you could just leave it in a warm place, or to speed it up, as before, you can heat it with your Bunsen burner. So I'm just going to get rid of the filter, and here's my evaporating basin. Put it on a heatproof mat again, and away we go, heating our copper sulfate solution to evaporate all the water off, to leave you with crystals. And like before, here's one I prepared earlier. You can see there's still some solution left in the bottom of that, but there's also some nice blue crystals of copper sulfate. And that's how you get a salt from an insoluble base. One big difference between the soluble base and the insoluble base is if it's insoluble, you filter off excess solid.